Hello guys, welcome back to my YouTube channel Anveshana Academy. This is Dr. Manjunath Chennapkot. Dear students, in the previous class we discussed what is conduction and how to calculate the conduction heat transfer and what equation we are using to calculate the conduction heat transfer in detail we have discussed. Dear students, come, we will move towards next topic. So that is real world examples for conduction heat transfer. Dear students, we understood what is conduction heat transfer. Then we will see some live examples for conduction heat transfer. So you can take first example, you can take, dear students, cooking. When you are cooking, right? So that cooking with help of metal plate. When the metal pot, okay, when the heat is going to transfer through a metal pot, that type of heat transfer you can call as a conduction heat transfer. That's also one of the conduction heat transfer examples. Next one, touching hot surface. If you are going to touch in a hot surface, then what will happen? There is a physical contact. If there is a physical contact, then what will happen? The heat is going to transfer from hot plate to your skin. That type of heat transfer you can call as a conduction heat transfer. Then metal spoon, dear students. Metal spoon in a hot liquid. If you are putting in a metal spoon in a hot liquid, then what will happen? Over a period of time, leave it for 1 minute or 2 minutes, what will happen? We are going to feel heat at one end. That means what? Here actually the hot water is here, but the spoon is dipped into the hot water. Over a period of time, leave it for 1 or 2 minutes or 5 minutes, then what happens? You are going to experience heat at this end. That means what? Heat is transferred from this point to this point. That if the heat is transferred from this point to this point through a metal body, that we can call as a conduction heat transfer. Hence what we can say, metal spoon in a hot liquid is also an example for what? Conduction heat transfer. Like that, ice pack on brews, that also you can take examples. Heating a room with a radiator, it's also an example for what? Conduction heat transfer. Like that, you can take heat sink, then you can take a touch screen phones, hot drink, okay, metal spoon and soldering iron. These all are what? Examples for what? Conduction heat transfer, dear students. Okay, now, so next topic, one of the important topic in conduction heat transfer is Fourier's law of conduction. Okay, so that what is that? Fourier's law of conduction. That's one of the important topic in the conduction heat transfer, dear students. What is conduction heat transfer according to Fourier? We will try to understand today. So dear students, what I will do, as I taken previously I have taken one example, that is what? Metal wire or metal rod. I started to heat at one end, so that heat is going to transfer from one end to another end. That is what conduction heat transfer. Okay, what is that conduction heat transfer? In detail we have discussed, but here that conduction heat transfer first well explained by a scientist. That scientist name is Joseph Fourier. He is a French mathematician. The name of the French mathematician is Joseph Fourier. Okay, what actually he is telling now, dear students, you can see here now. I have taken a metal rod. Okay, he has taken a metal rod. Then he is supplying certain amount of heat at one end. The heat is going to transfer from one end to another end. Then he is going to explain that rate of heat transfer in his own way. That means how it is, that you can see, dear students. So that means the amount of heat transfer or amount of heat transfer is directly proportional to amount of heat transfer, you can say, or the rate of heat transfer, that is Q, is directly proportional to cross-sectional area. That area must be perpendicular to the direction of heat flow. Dear students, when it comes to a rod, right, you can have two areas here now. One is surface area, you can have AS. Another one is cross-sectional area you can have. But when it comes to here a Fourier's law, that you have to consider an area, that area must be perpendicular to the direction of heat flow. Here, dear students, if you are supplying heat at this end, that means what? Perpendicular area will be the cross-sectional area that you need to consider. Hence, what he is telling them, the rate of heat transfer, that is Q, is directly proportional to cross-sectional area and its temperature gradient. What is temperature gradient? Change in temperature with respect to length of the metal rod or thickness of the metal plate. That is nothing but what? Temperature gradient. So that means what we can say there then? Fourier's law, what is the statement? The rate of heat transfer is directly proportional to cross-sectional area. That area is perpendicular to the direction of heat flow and its temperature gradient. That is nothing but what? Fourier's law of conduction. statement. Then equation for that is Q is equal to, what I can do, Q is directly proportional to A into dt by dx. Then he removed this proportional limit by using a constant. That constant we can call it as a k, dear students. So therefore what I can do here, what he has written equation, Q is equal to minus k into dt by dx. So why he has taken minus, dear students? When the heat is going to transfer from this end to this end, right, the temperature is going to decrease. The decrease in temperature is represented by a notation. That notation is negative sign, dear students. Yes. So what is Fourier's law of conduction here now? So what is the Fourier's law of conduction? The rate of heat transfer is directly proportional to its cross-sectional area, which is perpendicular to the direction of heat flow, and its temperature gradient. Then that proportional limit is removed with the help of a constant. That constant is K, where K is thermal conductivity. So therefore what he has done, he has written his statement in terms of equation, that is capital Q is equal to minus K into dt by dx. So what is K here, dear students? K is thermal conductivity of the given material. Then A is the cross-sectional area, which is perpendicular to the direction of heat flow. The unit for area is meter square, whereas unit for thermal conductivity is watt per meter Kelvin or watt per meter degree Celsius. Whereas dt by dx is what? Temperature gradient, that is nothing but a change in temperature, degree Celsius or Kelvin you can measure, where dx is nothing but what? Thickness or length of the material, so that is meter. Hence dt by dx is temperature gradient, and unit for temperature gradient is degree Celsius by meter or Kelvin by meter. This is what Fourier's law of conduction. So dear students, I will, to explain better, what I will do, I will take a rectangular metal plate or plain wall or plain, you can call, dear students, or some authors they will use word slab also. You can take anything else. So what I will do, I will take a metal plate. Okay, metal plate. What I will do, I will call this as a face A, and other side I will call it as a face B. Okay, phase A and phase B. Then what I will do, I will try to supply heat at one phase. That means what? Phase A. Then what happens? Then that phase A having any area, that area I will represent it as a capital A. Then that area must be perpendicular to the direction of heat flow. Dear students, when you are taking this metal plate, right, it is having area 1, it is having area here, it is having area here, and it is having area here, this side, this side, this side. But it is having a lot of areas, 6 areas it is having. But what we have to do, according to Fourier's, what we have to do, we have to take an area, that area must be perpendicular to the direction of heat flow. When you are supplying heat at this side, right, then if you are supplying heat at this side to the plate, then what you have to do, you have to take the area of what? Phase A. That means what? It is the length and width you can consider. That is that area is perpendicular to the direction of heat flow. One thing, and that plate having a thickness, that thickness we can represent with help of a notation, that is dx. Some authors they will take T, some authors they will take capital L also. That means what? Same thickness of the plate. Okay, then this is phase A and phase B. You can call it as a phase B. Then heat is going to transfer from phase A to phase B. That means what? The temperature is going to decrease. That to represent that, what I will do, at phase A I will mark it as a point 1, initial point. The heat is going to transfer from this point to this point. Okay, this point to this point. So initial point I will mark it as a point 1. The temperature at point 1 I will represent as a T1. Okay, the temperature at point 2 I will mark here as a T2. Once T1 minus T2 is nothing but what? Change in temperature, that is delta T, we can write, dear students. Okay, so that means what? Heat is flowing from phase A to phase B. Then phase A I will mark it as a point 1, that is a starting point or initial point, that I will mark it as a point 1. Then temperature at point 1 I will mark here as a T1. Temperature at point 2 I will mark it as a T2. So therefore what I can do now? So now heat is moving in from this side to this side. Dear students, one thing you have to observe here. Then when the heat is going to transfer from high temperature region to low temperature region, right, or phase A to phase B, because phase A is the high temperature region. Why so? Because the heat source is that particular point. That means what? Heat is flowing from this point. That means what? Phase A is the high temperature region and phase B is the low temperature region. That means what? Heat is going to transfer from T1 to T2. When heat is moving from T1 to T2, right, directly it will not move. There will be some resistance to the flow of heat. That resistance we have to mark. That resistance we can mark here as a R actually. So here initially it is having temperature T1. Then finally at phase B it is having temperature T2. So T1, T2, the same thing I can express. Whatever you are expressing here, right, in terms of resistance, that we can call it as a temperature with resistance. What we are expressing, right, that circuit we can call it as a thermal circuit. So how we can represent, dear students? At phase A, temperature T1 is there. Yes, I shown it. When heat is flowing through a metal plate, right, through metal plate, thickness of that metal plate, there is some resistance offered. That resistance I am going to mark here as a R. Then that R value is L divided by Ka. Then heat is flowing from T1 to T2. That I will show. Heat is flowing from high temperature region to low temperature region. Once the heat reaches point 2, right, that is temperature T2. So T1 and T2 are the temperature of metal plate at phase A and phase B, whereas R is the resistance to the heat flow. Then Q is the amount of heat flow or rate of heat transfer. This is what metal plate. So with the help of this, what we can do, we can calculate the rate of amount of heat transfer. How I can? So that with the help of a Fourier's law of conduction equation. Dear students, if the heat is getting transferred in a metal plate, how much amount of heat is getting transferred? That I can calculate with the help of an equation, that is Fourier's law of conduction equation. So initially the first scientist, that is Joseph Fourier, only given the explanation towards the conduction heat transfer. Based upon this experiment, based upon this explanation, based upon this law, we later started to calculate the amount of heat transfer in a conduction mode, dear students. Okay, this is Fourier's law. What is Fourier's law? Dear students, we can see here now. The sentence I have written it here. You can see the rate of heat flow through a simple homogeneous solid is directly proportional to the area of the section at right angles to the direction of heat flow. That means what, dear students? I can take a metal plate, that is solid metal plate. If I am supplying heat, or if I am transferring heat from this phase, that means what area, whatever it is there, that area I need to consider. Why? So it is normal or perpendicular to the direction of heat flow, and that material should be homogeneous, one thing. And temperature gradient, that is T1, here it is a T2. Change in temperature with respect to dx, it should be, that means what, again the rate of heat transfer is directly proportional to the cross sectional area, which is perpendicular to the direction of heat flow, and its temperature gradient, that is T1 minus T2 divided by dx. That statement of the Fourier's law. That statement he has given in terms of a mathematical equation, that is what, Q is directly proportional to A into dt by dx. Dear students, some authors they will take capital T as a temperature, some authors they will take small t as a temperature. It's up to you, but better to take capital T as a temperature and small t is the time. Okay, fine. Now, so that equation I can mark here as a Q is equal to minus K into dt by dx, where Q is what, nothing but what, rate of heat transfer, and K is thermal conductivity, unit is watt per meter Kelvin, and A is the cross sectional area which is perpendicular, and dt by dx is the temperature gradient. Dear students, for analysis what we will do, this is a isometric view, but analysis what we will do, we are going to take this phase for a analysis. That means what is the high temperature region, it is a low temperature region. So it will be here. So this only I will take for analysis, that I have drawn it here now. This I will assume it as a front view. This is my front view. I will take it. You see, this is a point 1 and it is a point 2. The temperature at point 1 I will mark here as a T1. Temperature at point 2 I will mark it as a T2. So then this phase I call it as a phase A. So I marked here phase A, and this side I marked as a phase B. So that phase B I am going to say here. I am going to show here, dear students, that is, this is phase A and phase B. Heat is going to transfer from phase A to phase B. That I have written it here now. Conduction heat transfer from phase A to B, dear students, and it is having a thickness. That thickness you can mark as a T, or you can mark it as a dx, or you can mark it as a L. It's up to you. And it is having an area. That area we can mark here as a A, or area. Then when it is a material, right, solid material, it's have its own thermal conductivity. That thermal conductivity you can mark as a K. That unit for thermal conductivity is watt per meter Kelvin, dear students. The amount of heat transfer you can represent as a capital Q. The unit for heat transfer is watt. That is nothing but joules per second, dear students. Okay, this is what Fourier's law of conduction. Okay, now while giving that statement, that means what, rate of heat transfer is directly proportional to cross sectional area, which is normal to the direction of heat flow, and its temperature gradient. This is a statement of Fourier's law of conduction. To give before giving this statement, he made some assumptions when he considered a metal plate. What are the assumptions he has made, dear students? You can take. So he has taken in a metal plate. He is trying to transfer heat from one place to another place. This is phase A he marked, and this is what phase B, dear students. Okay, phase B. It is a phase A. Heat is transferring from phase A to phase B. So then he has considered an area. That area is nothing but what? W into H. This is what W. This is what H. That he has considered. Then what actually he made some assumptions that you can see here now. Steady state heat conduction. Whatever the heat transfer is going to happen, right? There is a change in temperature. That temperature remains constant. So wherever you go and measure the temperature remains constant throughout the material. That he has made one assumption. And he made some second assumption as one dimensional heat flow. Dear students, when you are seeing, right, when you can see here now, I will come back. Okay, when you are transferring heat, right, in this direction, that means what? Heat is moving from left to right. That means what? In only one direction, x direction. So you can draw coordinates. Okay, this is x and this is y and this is z. Then what he has done, dear students, when the heat is transferring in a metal, right, there will be three directions. But what actually he assumed? He assumed heat is transferring in only one direction or one dimension, that too in x direction, not in y and not in z. Even heat transfer may be there in a y and z, but he assumed that heat is transferring in only one direction. That means what? He may insulate the body in other y and z direction. That means what? He assumed that heat is flowing in only one dimension or one direction. That he had made a second assumption. Okay, then third one, homogeneous and isotopic materials. The whatever the material is there, right, what he is transferring heat to the metal, right, that metal is homogeneous. That means what? It is made up of single material. That is what? Homogeneous material. And constant thermal conductivity. Dear students, you can measure thermal conductivity at this point, thermal conductivity at this point, thermal conductivity at this point. You can measure at any point. If it is the same material, thermal conductivity should be same in any point of the material. That is the one of the assumptions he has made. That means what? There should be constant in the thermal conductivity wherever you can take a point. One thing, I know heat generation. That means what, dear students? In the material there should not be any internal heat generation. If so, he assumed that while giving the statement, he assumed that there is no any internal heat generations in the body. It is what it's fifth assumptions. Like that he made some assumptions and he has given the statement. Okay, that plate you can show it here now. Dear students, if the heat is moving in from this side, that you can show it now. High temperature region you can mark here like this. It is a T1 and it is a T2. Why it's so? Because heat is going to transfer from high temperature region to low temperature region, where what happens? Temperature is going to decrease. Initially it was T1. When it comes to final state, right, temperature will be less. Hence, decrease in temperature we can show like this. Heat is moving from high temperature region to low temperature region. One represents high temperature region, two represent low temperature region for our reference, dear students. Then that plate having a thickness. So initial point I can mark here as a x1. Final point I can mark here as a x2. Then x2 minus x1 is nothing but thickness of the plate. When the heat is going to transfer through that material, right, it is having here initial temperature, that is T1. Here it is T2. When the heat is flowing in the metal, right, metal body, right, there will be some resistance. That resistance we can show it here now. So whatever the temperature and resistance you are showing in a circuit, right, that circuit we can call it as a thermal circuit, dear students. What is thermal circuit? Initial temperature is T1. Resistance offered in the material is represented as, that is the resistance. Then that resistance is nothing but what? R. That R value is R is equal to L divided by K into A. Then heat is moving from point 1 to point 2. The direction of heat flow you have to show. It is moving from high temperature T1 to T2. Then what is L here, dear students? The thickness of the material. Then what is K here now? Thermal conductivity of the material. Then what is A? That A means what? Area of the plate which is perpendicular to the direction of heat flow. Which is perpendicular to the direction of heat flow. These are the assumptions which are made before giving the statement of the Fourier's law. Okay, dear students, that you can say now. So metal plate, right? This is the area. The area is how to calculate the area. That's also important, right? That if you are taking this plate, it is having a height h and it is having a width w. Then what we need to do? This area I need to consider, not this area, not this area, not this bottom area, and not another area, this area. But what area I have to consider? I have to consider this area, because why? So it is perpendicular to the direction of heat flow. Hence what happens? The area is equal to what I can write now? That is a rectangular plate, right? W into HDS, students. T1 and T2, that I can show it in the thermal circuit. Then with the help of this Fourier's law of equation, we can determine the thermal conductivity also. How it is, that we can see here nowadays, students. We know the equation, conduction equation, right? So Q is equal to minus K into dt by dx. You can modify this equation. Then to take the value of K outside, then you are going to get the K value. That K value is nothing but thermal conductivity of the given material, dear students. Okay, so the same thing I have expressed. Heat is flowing in this direction. That heat flow is represented as a Q. Then that material having a thermal conductivity, that is K. That thermal conductivity can be represented as a K, and unit for thermal conductivity is watt per meter Kelvin. Heat is moving from high temperature region to low temperature region. That is high temperature we can mark as a T1 and T2 temperature. It is 0.1 and it is 0.2. You can mark, or phase A or phase B. The heat is moving in this direction, that we can show it in the circuit, thermal circuit diagram, dear students. This is about Fourier's law of conduction. I hope you understood today's class. If you understood, please do like, subscribe and support me. Thank you.